Hi, in this video I'm going to cover probability models for counts and normal probability model. And I'm going to cover chapters 11 and chapters 12 of statistics for business for decision making and analysis bias time. And please be sure to like, subscribe, and sign up for notifications on my channel, and so that you never miss our future videos. I will keep posting videos for these topics, especially videos for how to use Microsoft Excel and how to use Jump from SAS to solve problems. Alright, so let's start with the first slide. So we're talking about random variables for counts. And the main question, this is an example in the book. So saying, how many doctors should management expect a detailed representative to meet in a day if only 40% of visits reach a doctor? Is a rep who visits 8 or more doctors in a day doing exceptionally well? So to answer this type of questions, we need to use random variables for counts. So we need a discrete random variable to model counts and provide a method for finding probabilities. So one of these random variables is called Bernoulli random variables. So Bernoulli trials are random events with 3 characteristics, and these characteristics are you need to have 2 possible outcomes, and it can be success or failure, or yes or no, and you need to have a fixed probability of success, and that probability is normally given to you. If not, you can calculate it. It's just a simple calculation. And the events, these outcomes, should be independent, meaning that they don't influence on each other. So in the example that is available in the book, we will treat a visit to a doctor's office as a chance event with 2 possible outcomes. So the detailed rep either meets the doctor or does not meet the doctor. The success or failure of visit resembles a familiar random event like tossing a coin, and ideally 3 characteristics of these visits to the doctor resemble those associated with tossing a coin. And going back to Bernoulli random variable definition, this is a random variable B with 2 possible values. Can be 1, and we consider 1 for success, or it can be 0, and 0 represents failure as determined in Bernoulli trial. So the expected value or average of the random variable B, that is the success, that's a P, and that's a probability of success, and the variance of B, the random variable B, is probability of success times the probability of failure, which is 1 minus P. So P is representing success. All outcomes together will be 1, so the probability of failure is going to be 1 minus P. So this is in fact probability of success times the probability of failure. So a more important topic that is actually very similar to Bernoulli trials is counting successes. How many successes do we have, and we can actually predict the probability or calculate the probability of success by counting successes. And this is considered as binomial distribution. And let's consider y is your probability random variable. The sum of second Bernoulli random variables is a binomial random variable, which is the sum or the addition of each Bernoulli random variable. So y is also equal to number of success in n Bernoulli trials, and each trial with probability of success, which is given as p. So it's also defined by two parameters, n, which is the number of Bernoulli trials, and p is the probability of success for each trial. So in the example that we talked about earlier, we can define the number of doctors seen by pharmaceutical rep in 10 visits as a binomial random variable. This random variable y is defined by n equals to 10. So there are in fact 10 Bernoulli trials, and the probability of success and reaching a doctor is 40%. So we have an assumption, and that assumption is when we're using a binomial random variable to describe a real phenomenon, the 10% condition says that if trials are selected at random from a finite collection, it is okay to ignore dependence caused by sampling a finite population if the selected trials make up less than 10% of the collection. If you violate the 10% condition, you will need to learn about another random variable, and that's called the hypergeometric, and introduced in future exercises. But for this course, this is not a requirement, so feel free to study and read exercise 43 and 44 from the book. However, this is just optional, so you don't have to, and there won't be any questions on that in the future. But what's more important is when you are dealing with a binomial random variable, how to calculate mean, variance, and also we can calculate the standard deviation. So the expected value or mean of a Bernoulli random variable is equal to number of trials n multiplied by the probability of success p. So np, as simple as that. You don't need to go through lots of calculations. N is normally given, the probability of success is normally given, or it's really simple to calculate and just multiply them. And how about for variance? So variance is n, which is number of trials, times the probability of success, and times the probability of failure. So I said earlier that 1 minus p represents the probability of failure, since p is probability of success. So in this example, the number of trials is given 10 times, 10 visits, and the probability of successfully visiting a doctor is 40% or 0.4. So as a result, we expect a rep to see 4 doctors in 10 visits. How about the variance? How do we calculate the variance? That's n times p times 1 minus p, and that would be 1 times 0.4 times 0.6, and this should be a 10. So 10 times 0.4 times 0.6, which is 2.4, and that is your variance for this phenomenon. But we learned earlier that standard deviation, or SOD, or sigma, is square root of variance, right? So as a result, I can type here SQRT of variance equals to SD, where SD is the variance of Y. And let's just put it the other way to make it easier to understand. So this is standard deviation equals to square root of variance of Y, and that's 1 point. I'm going to make this smaller just to make sure it fits, and highlight it and bold. Okay. So and you know how to interpret standard deviation. A rep who has seen 8 doctors has performed 2.6 standard deviation above average. Alright, so in the next slide, we're talking about binomial probability that consists of 2 parts. So it consists of the probability of a specific sequence of Bernoulli trials with a Y success in n attempts, and the number of sequences that have Y success in n attempts, or the binomial coefficient. And as a result, we're going to have this formula. So the formula, the binomial distribution, or a random variable, is the binomial probability for Y success in n trials. If you want to calculate the binomial probability for Y success in n trials, you use this formula. And this formula is the probability of number of successes to be equal to small y is n chose y. This is a combination, and you have learned that earlier in the Stat 1 or Basic Statistics and Probability. And if for any reason you forgot that n chose r, what it is, we represent it this way, and it is in fact n factorial divided by r factorial times n minus r factorial. And what is factorial? When you multiply a number, let's say I say 7 factorial. I multiply 7 by lower natural values like 7 times 6 times 5 times 4 and until 1, right? So n factorial is n times n minus 1, n minus 2 times n minus 3 until 1. And r is r multiplied by r minus 1. You can calculate this value, right? And p is the probability of success. And y is, of course, how many success we are calculating the probability for in this topic. And 1 minus p is the failure. So if you have y success, how many failure do you have? Number of trials minus number of successes is number of failure, right? So this is the probability of failure to the power how many times failure we have. So if you have 10 trials and 4 of them were success, so this is probability of success to power 4, probability of failure to power 6, because 10 minus 4 is 6, right? So, and I will teach you how to use Microsoft Excel to calculate this, and you don't have to actually do anything. You just plug in the number of trials, you plug in the probability of success and also the y value, and Microsoft Excel will calculate this way. So the example that we have in the book is asking what is the probability of seeing 8 doctors in 10 visits by the rep? So number of trials n is 10. Number of successes that we are calculating the probability for is 8. And 10 minus 8 is 2. So probability of success to power 8, probability of failure to power 2. And that would, and remember that the sum of these two values, the power of success and the power of or exponent of the failure, the sum of them has to be n or 10, right? So that's equal to 0.011, and what does that tell us? This probability is about 1%. So 1/100th or 1%. Of course, this is rounded, but on exams, if the rounding digits or the decimals is given to you, pay attention to that and round the values accordingly. Now, on this slide number 14, if you read the book, you will see that we can ask the question in probability calculation in a different way. So the previous calculation that we had, here it says that what's the probability that exactly 8 doctors, we're seeing 8 doctors in 10 visits. But we also can ask a question like this: what's the probability of seeing 8 or more doctors, at least 8 doctors in 10 visits? At least 8 doctors, or seeing 8 or more doctors, means probability of seeing 8 doctors, or, and if you remember in probability theory, or means plus, so probability of 8 doctors, or 9 doctors, or 10 doctors. For each of these values, all you have to do is to go back to that formula and replace 8 with the 9, or 8 with the 10, and of course 2 will be accordingly changed, and the other values like 0.4, 0.6, these are probabilities, they are fixed. 10 is fixed. 8 will change. 1 time for 9, 1 time for 10, 2 for 9 is 1, and for 10 it's going to be 0. So look here. That's the probability of 8. We already calculated that. For 9, use 9 in the formula, and for 10, use 10 in the formula. And these are the numbers. For 8, it's going to be what we earlier calculated, 1%. This is 1,000ths. And this is, 0.1%. And this is 0.01%. And the sum of them, and of course you can see that the higher the value is going, the lower the probability. And the sum of them is 0.01229, and if the question say rounded by maybe you just use 2 decimals, right? So the answer would be 0.01, and 0.01 is a 1%. As a result, the probability of seeing 8 or more doctors in 10 visits is only slightly above 1%. This rep is doing exceptionally well. Alright, so the next slide is another example, very similar to what we learned earlier. Please read the book on this part, and it's just going to use different numbers and names, but it's just the same topic. The next topic that we need to talk about today is Poisson model. So the Poisson model, or a Poisson random variable, it describes the number of events determined by a random process during an interval of time or space. And it is not finite. The possible values are infinite, and it's defined by lambda, which is a Greek alphabet, the rate of events. So for example, the manager of a help desk that receives calls, if you asked this manager what's the probability of call arriving during the next second, in few seconds, how many calls are going to arrive? Of course, it's not easy for the manager to answer to this question, but if you change the question in a form of an interval of time, like how many calls are you expecting in 1 hour or in the next hour? So he probably knows, based on experience, based on past calls, that in 1 hour, how many, on a certain time of day, in 1 hour, how many calls he's receiving. So to address and answer to this type of problems, we can actually use the Poisson model. Or another example can be, we can have a rate for defects of product per square meter or malfunction per day in our products. So a Poisson random variable models the number of events produced by a random process during an interval of time or space. A Poisson random variable has, of course, one parameter lambda, and remember that when you pronounce it, that b is not pronounced, you say lambda, which is the rate of events. And for example, if you say you will receive 20 calls in an hour, then 20 is going to be lambda. And again, lambda is the rate of events or arrivals within disjoint intervals. If you were told we typically receive 90 calls per hour at this call center, then lambda is 90 calls per hour. And you can keep track of the measurement units on lambda, and they don't have to be an hour, they can be any interval of time. So in the next slide, slide 21, you can see that we use this formula to calculate the probability of x to be a certain value. So let's say you want to know, for example, we can say number of calls. So the probability of number of calls to be certain value. So that certain value is our small x, and that's normally the question. So maybe your manager wants to know what's the probability of number of calls to be 10 calls in the next 1 hour. You have to put 10 here. E is the natural value 2.7, E number, and lambda is the rate of arrivals. Where do we get lambda from? Lambda is actually calculated based on past data. So lambda here again, x is from the question divided by x factorial. And earlier in the previous slides, I said that factorial is multiplying this number by values lower than itself down to 1. So it's x times x minus 1 times x minus 2 until 1. So you just substitute the values and you find the numbers, and be happy again. You don't have to calculate these values yourself. Microsoft Excel or JUMP can calculate this for you. And at the end of this video, I'm going to show you both topics, that binomial distribution and Poisson distribution that you learned today. I will teach you how to use Microsoft Excel and JUMP to calculate these values. And of course, the expected value or average or mean for Poisson probability distribution is equal to lambda, and the variance is also equal to lambda. So the Poisson model uses a Poisson random variable to to describe counts of the data and is appropriate for situations like the number of calls or arrivals at the help desk or in an airport, in a 10 minutes interval or 30 minutes interval or 1 hour interval. It doesn't really matter. We can always change that interval. And let's have an example here. So this example is in the book. Please read the example, but it's a really quick. A supplier claims that its wafers have a defect per 400 centimeters square, and each wafer is 20 centimeters in diameter, and so the area is 314 centimeters square. What is the mean number of defects and the standard deviation? So the random variable, the number of defects on a randomly selected wafer, we can use a Poisson model here. So the assumed defect rate is 1 per 400 centimeter square, and since the wafer has an area of 314 centimeter square, the lambda is going to be 314 per 400 centimeter squares, and lambda will be 0.785. And to calculate the mean and standard deviation, you can calculate mean is equal to lambda. So let me just copy this here, and you know that variance is also the same, right? And I can just copy this and type here variance of x is also equal to the same value. And you know that standard deviation is the square root SQRT of the variance of x, which is SQRT of 0.785. If you calculate that, it's going to be 0.886. Okay, so we can see here that the next step is answering a question of probability. What's the probability of x to be 0, right? So no defects, and you can calculate that, and in the formula that you learned earlier, you just plug in 0 as lambda, 0.456 or 45.6%. So with that answer, we learned that the chip maker can expect about, so this is a round number of the 0.78 that we calculated earlier. So the chip maker can expect about 0.8 defects or 80% defects per wafer, and about 46% of the wafers will be defect free or without any defects. Alright, so we completed chapter 11, and next will be chapter 12. In addition, don't forget that at the end of this video I'm going to add a video on how to use Microsoft Excel to solve problems related to Poisson, and earlier you learned binomial probability distribution problems, and it's going to be very easy actually. Alright, so it's time for the next chapter. This is chapter 12, the normal probability model. And another kind reminder here that please be sure to like, subscribe, and sign up for notifications so you would never miss our future videos. I will keep creating videos on how to use Microsoft Excel and Jump to solve problems, so don't miss those new videos coming up in the future. A normal random variable. So let's look at this example. So Black Monday, October 1987, prompted investors to consider insurance against another accident in the stock market. How much should an investor expect to pay for this insurance? So this insurance cost called for a random variable that can represent a continuum of values, not counts. So for those of you who don't know the Black Monday, it was in 1987 in October. In the months began with a slight rise of stock prices and stock market, but the Friday, October 16, the market had gradually fallen to $2.9 trillion, and that drop was only a prelude, and on the following Monday the total value sank $500 billion, and many people lost a lot of money. So $500 billion evaporated in just one day. It's no wonder people call it Black Monday. So the sudden collapse left investors stressing over the possibility of another big drop in the future. Many decided to do something familiar like buying insurance. And if you drive, you have insurance in case you have an accident, right? So if you invest, you have insurance in case the market has an accident. That's what we meant by accident in this case. So insurance for the stock market provides coverage that pays you if the market stumbles. So how much should an investor expect to pay for this insurance? Your driving record affects your car insurance premium, right? So the same logic applies to insurance for stocks. If there is a significant chance that the market will take a dive, then insurance costs more. So based on what we learned in the past, we can't really model the stock prices or insurance problems, and this is because the price of stock is a continuous variable. It's not discrete, and as a result the changes are going to be continuously. So models for counts are not suited to amounts such as stock prices that can take on any of continuous of values. And that's the role of models based on random variables, such as so-called normal random that we're going to talk about in this chapter. So normal random variable is not the only continuous random variable. So the difference between this chapter and the previous chapter is we are mainly working and talking about making decisions about the continuous variables that there's no gap between events or outcomes. So this is an example of a histogram and a box plot created for the counts of 1 carat diamonds, or the prices of 1 carat diamonds. We can say that we sold in the past months, or we sold in the past 10 days. Okay, and this is another example of a normal distribution or histogram, where is about the percentage change in stock market. So this is the percentage change in stock market, and this is the counts. We have another example here, and that's X-ray measurements of bone density. So you can see that this is a random continuous normal random variable. It looks like a bell shape. So what is different between these three is that the units are different. So there's no zero here. That middle point, maybe you can find average or a median, and it falls somewhere here or here. And also for this one, maybe mean is around here, maybe median is around here. But the thing is, none of these three have the same measurements, right? So we need a way to standardize, creating a standardized random variable rather than having different measurements. So what's important for all normal random variables, we should have that bell-shaped. So you can see that from the previous histograms, all of those three cases, they had bell-shaped histograms, including the diamond prices and bone density and Black Monday of histogram of the market changes. So all three involve a continuous range of values. They all can be modeled using a normal random variable since they look like a normal shape. And what's the definition for a normal random variable? It's a continuous random variable whose probability distribution defines a standard bell-shaped curve. And this curve is supposed to be the perfect normal random variable looks like a bell shape, but it's perfectly symmetrical in the center, with respect to the center of it. Next is the central limit theorem. So the probability distribution of a sum of independent random variables of comparable variances tends to a normal distribution as the number of summed random variables increases. So it is no accident that many types of data have bell-shaped histograms. Any random variable that is the sum of enough independent random variables has a bell-shaped distribution. If the random variables to be summed have bell-shaped distributions to begin with, then it is not too surprising to learn that their sum has a bell-shaped distribution. What is also remarkable is that sum of just about any random variable eventually have a specific bell-shaped distribution, and that bell-shaped distribution is the normal distribution. So in the next slide, imagine we are tossing a coin. So if you toss a coin just 2 times, the probability of, for example, we have a, let's say, tail. If it's 1, the opposite is going to be 0. But if you toss it more, you have 5 trials, right? This creates a better normal shape as these probabilities are distributed well. And if you have more trials, 10 trials, that actually creates better shape of a normal distribution. So the larger the sample size, we can create a better normally distributed data. So the central limit theorem explains why bell-shaped distributions are so common. In fact, observed data are often accumulation of many small factors. Normal probability distribution is defined by parameters mu and sigma square. Mu represents mean average, and it's normally the center of the curve. And sigma square is considered as variance, or square of standard deviation. And the variance controls the spread of data around average. Now, earlier we said that different histograms that we saw in earlier examples, they all look normal, but they had different measures. So how can we standardize all of these different types of variables into one standard normal distribution where 0 is the middle point, or average is considered 0. So any average, doesn't matter what your measurement is, you can actually transform it into 0, and any sigma square or any standard deviation you can transform it to 1. So if you transform your average to 0 and your standard deviation to 1, you're actually bringing your curve to a standard normal distribution. So what is a normal probability distribution? A normal random variable is continuous and can assume any value in an interval, and the probability of an interval is area under the distribution over that interval. Remember that total area under the probability distribution is 1, and that's actually associated to the probability theory that maximum value for a probability is 1. So this is an example that we can calculate the probability that something happens between 0 and 1, right? So the probabilities are areas under the curve. And if you look at this picture here, you can see that we can have normal distribution with different mu's, and they all can be transformed to 0. Okay. So this is an example of different normal distributions with different values of variance. So when variance changes, you can see that the height of the normal distribution, or that bell shape, increases. And why is that? That's because the higher the variance or standard deviation, the higher the variation of data around mean. So if you have a higher variation around mean, mean is transferred to 0. If it's in 0, then higher values of standard deviation or variance actually create higher spread of data around the mean. And the smaller the value of standard deviation, the closer all your data are close to the mean, and that makes it a shape like the red color. So what is a normal model? A normal model is a model where the variable is used to describe an observable random process with average set to mean as the data and sigma set to s as standard deviation. So this is an example of a normal distribution. You can see that the average is a 4066, standard deviation of 738. Another example here for stock market, and another example here for bone density, right? So that normal shape, that's the perfect normal shape. And the question is how close this perfect normal shape is to the shape of the actual shape of the data. And the closer to it, of course, the better the normality of data. And this is the formula we use to standardize any normally distributed data into standardized normal model. So z equals to x minus mu. So that's how we transform to 0, right? Transform everything to 0 because we are subtracting average from x. So that's the average itself, average minus average, becomes 0. And we divide by sigma. So sigma divided by sigma is 1. So that's transferring it to 1. So the standardized normal probability is where mean is 0 and standard deviation is 1. So we have an example here let's say the average is 4066, standard deviation is 738. What is the probability of x to be more than $5,000? Right? So all we need to do is to transfer to 0 and 1. So subtract x to be more than 5,000. So x minus mu divided by sigma. To be greater than, on both sides we subtract mu, and on both sides we divide both sides by sigma. We do that, that would be 5,000 minus mu average, 4066 from here, and divide by 738, which if you calculate it, that's 1.27. So we are actually, to calculate the probability of x to be more than $5,000, or the price of the diamond to be more than $5,000, we actually can calculate the probability of z, which represents the standard normal distribution, to be more than 1.27. And looking here, let's say 1.27, and we can actually look at a z-table, and from z-table we can calculate this probability. So let's see, in that question we have it's z greater than 1.27. So if this is, for example, 1.27, that area to the right would be the answer. So let me bring in a z-table. So this is the z-table. And so the area provided here is area all to the left of a z value. What we want is 1.27, and it's greater than 1.27. So that's the right hand side. So whatever the left hand side is, 1 minus of this area is equal to that white area. So I go here 1.2, 1.2, and I want 1.27. So the 7, that next decimal, I can take it from up here, 0.7, add it to 1.2, so 1.2, and 7 is up here, right there. The value is 0.8980, that value. And this is area to the left of 1.27. I want greater than 1.27, so 1 minus 0.8980 is my answer, which is probably 0.112, somewhere around there. Okay, so we can actually calculate that, but that's just as easy as that. Okay, so these next slides are going to remind you of empirical rule that we talked about in the previous chapters. When I was teaching standard deviation, I explained the empirical rule, and I told you if you have a normally distributed data, then one standard deviation from the mean covers 68%. 2 standard deviation away from the mean, that interval of 300 to 700 covers 95% of our observations, and 3 times standard deviation away from the mean covers 99.7% of your observations. And this is actually the same thing. Alright, so this is another example. A math sat score of 600 is equivalent to z equal to 1. Using empirical rule, we can find that 15.85% of test takers score 600 or better. 600 or better. And later I will teach you how to use Microsoft Excel to calculate the normal distribution values. And in this slide 29, you can see that if you want to calculate the probability between z to be between two values, always find the probability of the higher value, 1, from the z table that I showed you, minus the smaller value, the probability of z to be a smaller value. Then you can find the difference in between those two, and that's the area, right? So it's 0.8 minus 0.3, that's 0.5. Alright, so this is another example. I remind you that this is a review session, so I won't go into much details as you have learned these topics in details earlier. So this is just another example, and please read the book on these examples and practice with Microsoft Excel. And a few definitions here. I've already talked about skewness and outliers in the past, but just to remind you really quick, multimodality is when you have more than one mode, and mode is the most frequent value in your dataset. Skewness is lack of symmetry, when the shape of your histogram does not fit that perfect bell shape of normal distribution. There is a possibility of a skewness to the right or left, and that's because you probably have some values higher to the right or high to the left of your data, and they are actually affecting your average, and average is being skewed to the right or left. And you normally see a longer tail on right or longer tail on the left. What are outliers? So if any unusual extreme values to the right or left of your data, those are considered outliers. So normally we use, if we say like 3 times standard deviation, after 3 times standard deviation, if you have a value higher than or lower than 3 times standard deviation to the right or left of average, that's where we can say there's an outlier. But I will in the future, in the future videos, you will see that I will explain outlier. We will use JUMP and use some higher level analysis and learn how to recognize outliers using JUMP. And some results and departures from normality is normal quantile plot. So normal quantile plot, it helps us in diagnostic scatter plot used to determine the appropriateness of a normal model. If the data track the diagonal line, the data are normally distributed. So let's see an example here. So we're going to see if these two are, if there is normality, all those points coming from these two will fall on that line. And in this case, you can see that we expect to see, if there is normality in data, all these points fall on that line, not going outside of that range, lower of that upper curve and higher than that lower curve. So if all these points fall on the line, or at least between the two curves, we can say that it indicates normality of data. Okay, so here you can see that majority of this data are actually out of the line, so you don't see normality here. You can see that how many outliers are, can't confirm all of them are outliers, but they seem to be outliers. They're the ones that are creating that abnormality. And skewness, as I've said before, it represents lack of symmetry. And if the value of skewness, or SK or K, is 0, we have no perfect normality. And there are different methods you can use to calculate skewness. Both JUMP and Microsoft Excel calculate skewness for us. Actually, we don't need to calculate it ourselves. So you just have a data set. You can calculate, like you can calculate the average, you can calculate the standard deviation of data, you can also calculate the skewness of data. So if it's 0, we have a normal data. If it's not 0, it's not it is skewed. But up to a certain point, we can also consider skewness, non-zero skewness, to be a normal distribution for certain tests, and we will talk about that in the future when we get to regression analysis. This is just another example, and that's chapter 12. So the next step will be we will talk about the I'll show you how to use Microsoft Excel to get answers for problems associated to the topics we talked about today. Both of them, the probability model for counts, binomial distribution, Poisson distribution, and normal probability distribution. All of them will be explained in the next steps. Alright, so let's have an example so we can solve this problem using Microsoft Excel. So it's saying that a study in June 2003 by Illinois Department of Transportation concluded that 76.2%, so 76.2% of front seat occupants used seat belts. A sample of 12 vehicles is selected. How many samples? 12 samples. What is the probability the front seat occupants in at least 7 means 7 or 8 or 9 or 10 or 11 or 12 vehicles are wearing seatbelt, right? So how do we solve this problem? We look at the problem is this way: probability of x to be more than 7, and more than 7 means where number of trials is 12. Probability of success here is 0.7. Success means they use seat belt, right? 0.762. So probability of 7 cars are using seat belt, plus probability of 8 of them, plus probability of 9 of them are using seat belt, 10, 11, or 12. And or means plus, so we're adding these events, right? Outcomes. So let's see where those numbers came from. Okay, so let me bring in Microsoft Excel and show you how to calculate these values. Okay, so here I have all possibilities for a value of x. Let's make this a little larger. And also we can calculate the probability of x, or px. And here I'm going to enter the formula for our binomial probability. So just need to check the probability is 76.2. So that would be equal to, so this is a binomial distribution, right? So I type binom.dist and double click binom.dist, and it's saying number. What number? 0. Of course we want after 7, but we can calculate even from 0. Okay, so we can type in binomial distribution. So the first value is x, and later when you copy, x is going to change to 1, 2, 3, 4, and can calculate it down to 12. And the second one is number of trials, and that's how many samples we got here. We got 12 samples, right? And the probability, the next one is the probability of success, which is saying 76.2%, right? Based on past data, they know that 76.2% of people are using seatbelt. As a result, remember probability in Microsoft Excel, this probability is supposed to be presented as a decimal value. So if it's 76.2% divided by 100, that becomes 0.762. And on cumulative, you're going to the next one you're going to choose false. Use false because this is not a continuous distribution. It's not cumulative. It's just for exact 0 if the probability is probability of none of those people using seatbelt. No one uses seatbelt. In 12 trials with the probability of sitting belt is 76.2%. That's exact just for 0. It's not between two values. So we don't want cumulative. We just want for value of 0. And for the rest, you just need to copy the formula. So I just double click on this if you want to check it again. And then I press enter, and bottom right of the cell when it's a black plus, click, hold, and drag down. It's going to copy the formula for all of these values. Don't forget to write these values at the beginning before you calculate the probability of x. If there is no values here, all of them are considered 0, because if a cell doesn't have a value, Microsoft Excel considers it as a 0. So make sure you type in these numbers first and then calculate the probability. Now let's look at my values versus the values on these slides. So probability of x equal to 7. So 7 is here. 7 to 12, right? 7 to 12. Let me highlight it with a maybe different color. Alright, 7 is 0.0902, 0.0902, nice. 8 cars are having seatbelt, right? 8 is 0.1805, 0.1805. So that's correct. And we said that we need the sum because either this one or this or up to 12, right? So we just need to calculate the sum. Sum x to be equal to 7 dot 12, that means from 7 to 12 equals to, so type equal to sum and just select the values you want to add. And that's it. It's going to calculate the total probability here. Press enter. 0.09563. 0.09563 is the same number. Okay. So, and if you want to reduce the decimals, you can do that actually. Alright, so let's just all in the center. So that's your sum. It's the probability of x to be equal to 7 plus probability of x to be equal to 12. Okay, that looks better. Okay, so that's how you do binomial using Microsoft Excel. The next is going to be Poisson Distribution. Alright, so I have an example for Poisson Probability Distribution here. Assume baggage is rarely lost by Northwest Airlines. Suppose a random sample of 1,000 flights shows a total of 300 bags were lost. Thus, the arithmetic mean number of lost bags per flight is 0.3. How did we get the 0.3? That 300 divided by 1,000. That's a probability, right? 300 divided by 1,000, that's 0.3 or 30%. And if the number of lost baggage per flight follows a Poisson distribution with mu equals to 0.3, find the probability of not losing any bags. Not losing any bags means 0, right? X is 0. So let's use Microsoft Excel and calculate this. Okay, let me open my Microsoft Excel and bring it in. Okay. And let me check my numbers one more time. So 0 and 0.3. And the answer has to be 0.7408. Okay. So you simply just need to type equals to. So it's a Poisson Poisson distribution of x. So what is x here? X is 0 because we want to find the probability that none of those bags get lost, right? 0, none of them. And what's the probability, or what's the average luggages being lost? That's 30%. So 30%. Make sure, if it's given in percent, make sure to change it to decimal. So you give a value in decimal, 0.3. And remember that topics we covered in chapter 11, they are not continuous, they're discrete, right? As a result, do not use for cumulative. We don't want cumulative. If it's for normal distribution, it's cumulative. So you put true. For discrete distributions like Poisson distribution, like binomial, you use false. So this is a false. Because just for the point 0, it's not between any 2 points, or less than or more than. It's just 0 itself. So use a false. And you press enter. That's your probability that is calculated here and down here. So look, you don't need to do any calculations for Poisson or binomial problems. Everything is on Microsoft Excel. Just double click and find a number. It's the same number that we have here. 1 decimal, I can reduce the decimals. Okay. So next will be, I will show you how to find normal probability distribution values using Microsoft Excel. Okay, for normal distribution. Alright, so here we have a few examples. The weekly income of shift foreman in glass industry follows the normal probability distribution with the average of $1,000 and a standard deviation of $100. What is the z value for the income, let's call it x, of a foreman who earns $1,100 per week and $900 per week? So for each one we can calculate here 1,100 minus $1,000, x minus average divided by standard deviation is 1. So z is 1. For x equal to $900, that's 900 minus 1,000. So the 1,000 and the 100, they are fixed. They don't change. X is always changing, right? So that's negative 1. So if we look at this in so this calculation is easy. You don't need the Microsoft Excel for this, but if you want to do it using Microsoft Excel, let's just use it this way. So here we can write a z equals to, and here we can write, let's say x is given, and then mean is given, and standard deviation is given. Right? And the z is what we want to calculate. What is z? Okay, x is, in this case, one of them is $1,100, and average is $1,000. Standard deviation is $100. What is z? Z equals to x minus 1,000. And we need a parenthesis because order of operations will divide first. So we don't want to let that happen. Parenthesis has to be first and divide by this value. So it's 1. You can do the same thing for 900, right? You just need to change this to 900. That's negative 1. So you always can just change this number. This 2 can be fixed. You just change x, and that's going to give you z. Okay. Of course, different scenarios, they create these different values, but well, I can say that this is going to work anyway. Alright. I want this to be right. Okay. Alright. So 1 and negative 1. And I can also create it for 1000 or 1100 next to it, just to have it. Equals to, these are given 1000 and 100, and equals to, so 1 parenthesis this minus average parenthesis close divide by 100. Okay, so have these values, and let's just say, if the question says what's the probability that a foreman, we select a foreman and that foreman earns between 900 to 1100, right? If that's the case, then we're calculating the probability of a foreman who is earning between 900 to, so x is between 900 to $1,100. Since we already calculated z, this is in fact equivalent or equal to the probability of z to be between -1, z, and 1, positive 1. And that's equal to, so we can actually calculate that here. So that's equal to probability of z to be equal to 1. Remember, Microsoft Excel, when you calculate the normal distribution, it gives you area all to the left of any point of z you give it to. Okay, this is equal to minus the probability of, so larger value minus the smaller value. Z equal to -1. Oops, -1. That's equal to, so what's the probability that z is equal to 1? So let's calculate that here. Equal to, or maybe we can calculate them here first. Probability of z to be, so I said less than, so less than 1 minus less than -1. That will be between 1 and -1. So that of the less than 1, probability of z less than -1, right? So that's equal to norm. So that's a standard, because z is a standard. If it's not a standard, if you just want to use x values, you use norm.distribution, but we want norm.s.distribution. And it's just asking for z. What is a z? 1. Is it cumulative? Yes, because it's a continuous variable. So close it. True. True is because it's a, you want to see area under the curve all to the left. All to the left of 1, right? Press enter. And for this one, it's equal to, this is the same actually, norm.s.distribution of -1. and true. Okay. So I said this, the difference between these two. The difference between these two is the probability of z between -1 and 1 equals the difference of these two. That's equal to this minus this, which is 0.68%. Okay, so that's how you calculate these probabilities. If they ask you what's the probability of, let's say, question says what's the probability of person, we select a person, that person makes more than 1100, the of z to be more than 1100, and 1100, z for 1100 is 1, so more than 1. For more than 1, it's okay. So that's the opposite, right? Excel give us less than 1. We already know for less than 1. Opposite, more than 1 will be 1 minus less than 1, and we already know what is the less than 1. So we just type equal to 1 minus whatever we calculated up here of less than 1. 1 minus less than 1 is more than 1, okay? So that's 0.15. And this is how you actually can make all those calculations. Yeah. So you just need to practice with different type of problems and understand how to solve problems. And at the end, please don't forget to subscribe, and please don't forget to sign up for notifications, like the video, and I just want to make sure you will see my future videos that I will upload. I will keep creating videos on how to use Microsoft Excel and Jump.